There is something peculiar about the way the universe looks from where we stand, something that took astronomers decades to notice and even longer to accept. It is not a dramatic anomaly that announces itself with flashing lights or obvious contradictions. Instead, it is a quiet discrepancy, a gentle wrongness that hides in the spaces between stars, in the patterns of galactic motion, in the arithmetic of cosmic distances. And once you begin to understand it, the universe never quite looks the same again. Consider for a moment how strange it would be to learn that your hometown sits in an unusual location on Earth. Perhaps you always assumed it was typical, just another point on the map, unremarkable in its geography. But then someone shows you the data, and you realize that your town occupies a peculiar depression, a basin where the land dips lower than almost everywhere else for thousands of miles in every direction. The discovery would not change your daily experience of walking the streets or feeling the wind, but it would transform your understanding of where you are and what surrounds you. Something similar has happened to humanity's understanding of our cosmic address. For generations, we assumed the Milky Way occupied an ordinary spot in the universe, a typical location amid the vast scatter of galaxies. This assumption was not careless. It was built into the foundations of modern cosmology, a principle that stated the universe should look roughly the same from any vantage point when viewed on the largest scales. And for the most part, this principle seemed to hold true. But the universe, as it so often does, had a surprise waiting in the data. Before we explore what that surprise revealed, there is something we need to understand about how astronomers perceive the cosmos. We cannot walk through the universe. We cannot send probes to distant galaxies and have them report back within our lifetimes. Everything we know about the large-scale structure of space comes from light, from photons that have traveled for millions or billions of years before reaching our telescopes. This light carries information, but that information requires interpretation. And interpretation requires understanding the medium through which the light has passed. Imagine trying to understand the shape of a landscape by listening to echoes. You stand in one place and shout. Then you listen carefully to how your voice bounces back from distant surfaces. With enough echoes and enough patience, you could begin to construct a map of your surroundings. But if the air itself had unusual properties in your immediate vicinity, if it bent sound in unexpected ways or absorbed certain frequencies preferentially, your map would be distorted without your knowledge. You would need to discover and account for those local conditions before your map could accurately represent the wider world. Astronomers face a similar challenge. The light that reaches us has passed through the environment immediately surrounding our galaxy before it arrives at our instruments. If that environment is unusual in some way, our measurements of the wider universe could be systematically skewed. For a long time, scientists assumed our local environment was unremarkable, just average cosmic space. This assumption seemed reasonable, even humble. It avoided the ancient trap of placing humanity at a special center of creation. But what if the assumption was wrong? Not because we are at the center of anything, but because we happen to occupy an unusual margin, an edge, a deficit in the cosmic fabric. And this brings us to another quiet detail that gradually became harder to ignore. When astronomers measure distances to faraway galaxies, they often use objects called Type Ia supernovae. These are stellar explosions that reach a consistent peak brightness, making them useful as cosmic yardsticks. By comparing how bright a supernova appears to how bright it actually is, astronomers can calculate how far away it must be. This technique has been refined over decades and has produced some of the most important results in cosmology. But distance is not the only thing that matters. Astronomers also measure how fast galaxies are moving away from us by examining the stretching of their light towards redder wavelengths. The combination of distance and velocity allows scientists to calculate the expansion rate of the universe, a number known as the Hubble constant. This constant is fundamental. It tells us how quickly the cosmos is growing, how old the universe might be, and how its expansion has evolved over billions of years. Here is where the quiet trouble began. Two different methods of measuring the Hubble constant should, in principle, give the same answer. One method looks at the nearby universe, measuring supernovae and other standard candles within a few 100 million light-years of Earth. The other method looks at the oldest light in existence, the cosmic microwave background radiation that was released when the universe was just a few 100,000 years old. Both approaches are extraordinarily precise. Both have been refined and cross-checked by independent research teams around the world. And yet, they disagree. The nearby measurements suggest the universe is expanding faster than the distant measurements indicate. The discrepancy is small in absolute terms, roughly 9%, but it is far larger than the uncertainties in either measurement should allow. If both methods are correct, and there is no obvious reason to doubt either one, then something about our understanding of the universe must be incomplete. For years, cosmologists searched for errors. They looked for calibration mistakes, observational biases, and unaccounted systematic effects. They scrutinized every step of both measurement chains. Some small corrections were made, but the fundamental disagreement persisted. The tension became famous in scientific circles, a puzzle that refused to yield to conventional explanations. And this is where the nature of our cosmic neighborhood begins to matter in a profound way. Let us drift a bit deeper into this idea. If the Milky Way resides in a region of space where matter is less densely packed than average, the gravitational dynamics of our local environment would differ from cosmic norms. Galaxies within this underdense region would experience weaker gravitational attraction pulling them back, allowing them to coast outward more freely. This added velocity, layered on top of the universal expansion, would make nearby space appear to expand faster than it truly does on the cosmic average. This is not speculation. It is gravitational physics applied to inhomogeneous distributions of matter. The effect would be subtle but real, and it would specifically affect measurements made from within the underdense region, while leaving the ancient cosmic microwave background largely untouched, since that light originated long before the local structure formed. The question, then, is whether such an underdense region actually exists around us. And the answer, gradually assembled from decades of galaxy surveys and careful analysis, is yes. Our galaxy appears to lie within an enormous expanse of relatively empty space. This region extends outward for roughly 1 billion light-years in every direction, encompassing everything we casually think of as nearby in cosmic terms. Within this volume, the density of galaxies and matter is measurably lower than the cosmic average, perhaps by 15 to 20% depending on which survey you consult. This is not a trivial difference. A 20% reduction in matter density over such a vast scale represents a significant departure from the uniformity that cosmology assumes. It means that when we look out at nearby galaxies and measure their velocities, we are observing a sample that is subtly but systematically influenced by this local deficit. But before we continue, there is something we need to understand about how such structures come to exist in the first place. The universe was not born perfectly smooth. In its earliest moments, quantum fluctuations created infinitesimal variations in the density of matter and energy from place to place. These variations were tiny, perhaps 1 part in 100,000, but gravity is patient. Over billions of years, gravity amplified these small differences. Regions that were slightly denser attracted more matter, growing denser still. Regions that were slightly less dense lost matter to their surroundings, becoming progressively emptier. This is how structure emerged from the primordial uniformity. Dense regions collapsed into galaxies, which gathered into groups, which aligned along filaments, which intersected at massive junctions. Meanwhile, the underdense regions expanded and emptied, becoming vast volumes where gravity lost its grip and matter grew sparse. The result, after 13 billion years of evolution, is a universe that resembles a three-dimensional web. Luminous matter concentrates along strands and sheets, while enormous voids occupy the spaces between. This web is the largest pattern in nature, stretching across billions of light years, and it is within one of its voids that our galaxy appears to have found its home. What does this imply for our understanding of the cosmos? If our measurements of cosmic expansion are influenced by our local environment, then the apparent disagreement between nearby and distant methods might not indicate new physics at all. It might simply reflect the fact that we are observing the universe from an unusual vantage point. The true expansion rate of the cosmos could be the value indicated by the cosmic microwave background, roughly 67 kilometers per second per megaparsec, while the higher value from nearby supernovae could be a local distortion caused by our underdense surroundings. This would be a profound resolution to the Hubble tension. It would preserve the standard cosmological model while explaining the discrepancy as a consequence of cosmic geography rather than unknown forces or particles. But it comes with a philosophical cost. It requires accepting that our location in the universe is not entirely typical, that we happen to occupy a relatively unusual position within the cosmic web. For scientists who value the cosmological principle, this is an uncomfortable conclusion. The principle states that no place in the universe is special, that the cosmos should appear homogeneous and isotropic to any observer when viewed on sufficiently large scales. Discovering that we live in a significant underdensity does not necessarily violate this principle, since underdense regions are a natural part of the web and must be inhabited by someone. But it does suggest that our observations might be less representative of cosmic averages than we previously assumed. And this brings us to another quiet detail that deserves attention. The motion of galaxies through space is not determined solely by the expansion of the universe. Gravity from surrounding structures also influences how galaxies move. These additional motions, called peculiar velocities, can be measured by comparing a galaxy's observed redshift to the redshift expected from pure cosmic expansion at its distance. The difference reveals how gravity has pushed or pulled the galaxy relative to the cosmic flow. When astronomers measure the peculiar velocities of many galaxies across large regions of space, they can map the gravitational landscape of the cosmos. Regions of high mass pull galaxies toward them. Regions of low mass allow galaxies to flow away. By reading these motions like the currents in a vast three-dimensional ocean, scientists can infer the distribution of matter even when that matter is invisible. This technique has revealed structures of staggering scale. One such structure lies in the direction of the constellation Centaurus, a massive concentration of galaxies and dark matter that exerts a gravitational pull felt across hundreds of millions of light years. Our galaxy, along with countless others, is drifting toward this concentration at hundreds of kilometers per second. The direction and speed of this motion have been measured with increasing precision over the years. But the motion toward this attracting mass is only half the story. Gravity can also be thought of in terms of what is absent rather than what is present. An underdense region, a void, exerts what might be called a gravitational push, though the physics is more accurately described as a reduced pull. Galaxies near a void are attracted more strongly by the denser regions on the opposite side, causing them to accelerate away from the emptiness. The effect is as real as any gravitational attraction, just operating in the opposite sense. When astronomers analyzed the peculiar velocity field around our galaxy with sufficient precision, they discovered something unexpected. Our motion through space is not adequately explained by attraction toward massive concentrations alone. There also appears to be a significant component of motion away from an underdense region behind us, a void-driven repulsion that contributes to our galaxy's overall trajectory. This repelling void, sometimes called the dipole repeller, was identified by carefully subtracting the known effects of attracting masses and examining the residual motion. The analysis revealed that we are being pushed away from a particularly empty region of space, even as we are being pulled toward particularly dense regions elsewhere. The interplay between these attractions and repulsions shapes the flow of galaxies throughout our cosmic neighborhood. Why does this matter? It matters because the existence of a significant local void, combined with the gravitational effects it produces, reinforces the picture of our galaxy occupying an unusual position within the cosmic web. We are not at the center of anything, but we are embedded within a notable underdensity that influences our observations and our motion through space. Let us drift a bit deeper into this idea. The cosmic web is not a static structure. It is constantly evolving, with matter flowing along its filaments, falling into its dense nodes and evacuating its voids. This flow is governed by gravity, which itself depends on the distribution of matter. So there is a feedback loop. Structures shape the gravitational field, which guides the flow of matter, which further shapes the structures. This process has been operating for billions of years and will continue for billions more. Within this dynamic framework, voids occupy a curious position. They are regions where the cosmic clock runs slightly differently. Because matter is sparse, gravity is weak, and the resistance to cosmic expansion is minimal. Dark energy, the mysterious component that accelerates the expansion of the universe, finds little opposition in these empty reaches. As a result, voids expand faster than the cosmic average, stretching and growing over time. This differential expansion means that voids are not merely passive absences of matter. They are active participants in cosmic evolution, pushing against their surroundings and influencing the behavior of nearby structures. The filaments that border a void are squeezed between the void's expansion and the gravitational pull of denser regions, creating a complex interplay of forces that shapes the cosmic web. If our galaxy lies within such a void, we are participating in this expansion. The galaxies around us, those that share our underdense environment, are all moving apart from one another slightly faster than they would in a region of average density. This is not because space itself is expanding at different rates in different places, though in some sense that is one way to describe it, but because the local gravitational environment permits faster separation than denser regions would allow. And this is where the measurement of cosmic expansion becomes delicate. When we observe nearby galaxies and measure their recession velocities, we are sampling this local environment. If that environment is expanding faster than average due to its underdensity, our measurements will reflect that anomaly. We will infer a higher expansion rate than the cosmic average, not because our measurements are wrong, but because we are measuring local conditions that differ from global ones. The resolution of the Hubble tension in this interpretation lies not in exotic new physics, but in careful accounting for our position within the cosmic web. We need to understand our local environment well enough to correct for its influence on our observations. Only then can we accurately infer the true expansion rate of the universe as a whole. But this raises a challenging question. How confident can we be in our understanding of the local void? How precisely have we mapped its extent, its depth, its shape? And this brings us to another quiet detail that deserves our attention. Mapping the distribution of matter in the universe is extraordinarily difficult. Galaxies are visible, yes, but they trace only a fraction of the total mass. The majority of matter in the universe is dark, invisible to our telescopes, detectable only through its gravitational effects. To truly understand the cosmic web, we need to map not just the galaxies, but the dark matter that surrounds and underlies them. Several techniques allow astronomers to probe the distribution of dark matter. One involves measuring the weak gravitational lensing of distant galaxies by intervening mass. When light from a distant source passes near a concentration of matter, gravity bends its path slightly. By measuring the subtle distortions in the shapes of millions of distant galaxies, astronomers can reconstruct the distribution of foreground mass that caused the bending. This technique has been applied to enormous surveys, mapping the dark matter distribution across significant fractions of the sky. The results confirm the web-like structure of the cosmos, with dense filaments connecting massive clusters and voids appearing as regions of minimal lensing signal. Within this framework, the local underdensity around our galaxy is consistent with occupying a relatively empty cell of the web. But weak lensing measurements are challenging near our own position. We cannot easily measure the lensing effect of matter that lies between us and nearby galaxies, because those galaxies are too close for the effect to accumulate significantly. Our understanding of the immediate local environment comes more from galaxy counts and peculiar velocity measurements than from lensing. Another approach involves measuring the cosmic microwave background radiation. This ancient light, released when the universe was just a few 100,000 years old, carries imprints of the density fluctuations that would later grow into the cosmic web. By comparing the predicted properties of the microwave background with observations, cosmologists can constrain the overall parameters of the universe. But there is a subtlety. As the microwave background light travels toward us, it passes through the structures that have formed since its release. These structures affect the light in measurable ways. Regions of high density cause slight heating of the photons through a process called gravitational redshifting, while voids cause slight cooling. This effect, known as the integrated Sachs-Wolf effect, provides another window into the distribution of matter along our line of sight. Observations of the microwave background have revealed tantalizing hints of an unusual coldness in certain directions, consistent with the light having passed through particularly large voids. Whether this coldness correlates with the local underdensity around our galaxy remains a subject of investigation, but it suggests that the methods for probing our cosmic environment are beginning to converge. How could this be possible? This convergence of independent lines of evidence toward a common picture. It is possible because the universe, despite its complexity, is governed by consistent physical laws. Gravity behaves the same way everywhere. Light follows predictable paths. The cosmic web, vast and intricate as it is, obeys the same mathematics regardless of where you observe it from. When multiple independent methods point toward the same conclusion, confidence grows that the conclusion reflects reality rather than coincidence. And the conclusion, increasingly, is that we inhabit a significant underdensity. Let us pause here for a moment and consider what this means in broader terms. For most of human history, our species had no awareness of the cosmic web. We did not know that the universe was expanding, that galaxies existed beyond our own, or that space itself could have structure on scales beyond comprehension. The discovery of our place within this web is an achievement of the past century, a testament to the power of careful observation and mathematical reasoning. But with that achievement comes humility. We now understand that our vantage point is not privileged. The cosmos looks different from different locations. What we observe is filtered through the lens of our position, our motion, our local environment. Extracting universal truths from local observations requires disentangling these effects, correcting for our particular circumstances to reveal the underlying reality. This is harder than it might sound. We cannot travel to another location and check our observations against a different perspective. We are bound to our place in the Milky Way, observing the universe from within whatever environment surrounds us. The best we can do is model that environment as accurately as possible and adjust our conclusions accordingly. And this brings us to another quiet detail that connects our local situation to the largest questions in cosmology. The cosmic microwave background provides a snapshot of the universe when it was very young. By studying the patterns in this ancient light, cosmologists have determined the fundamental parameters that govern cosmic evolution: the density of matter, the density of dark energy, the rate of expansion, the overall geometry of space. These parameters, collectively known as the cosmological model, form the foundation of our understanding. But there is a tension within this foundation, a tension that the local void might help explain. When cosmologists use the parameters from the microwave background to predict what the local universe should look like, the predictions do not quite match the observations. The discrepancy is subtle but persistent. Nearby galaxies appear to be moving slightly faster, structures appear to be slightly more pronounced, and the expansion rate appears to be slightly higher than the cosmic model predicts. One interpretation is that the cosmic model is incomplete, that new physics is needed to explain the discrepancies. But another interpretation is that the cosmic model is correct on average, while our local environment deviates from that average in ways that affect our observations. If we live in an underdensity, our local measurements will naturally deviate from cosmic predictions without implying any failure of the underlying model. Distinguishing between these interpretations requires knowing our local environment with great precision. It requires mapping the distribution of matter within hundreds of millions of light years, modeling the gravitational effects of that distribution, and calculating how our observations would be affected. This is an enormous undertaking, involving some of the largest galaxy surveys ever conducted in sophisticated computational simulations. Progress is being made. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies in 3 dimensions, revealing the web-like structure of the cosmos with unprecedented detail. Simulations using supercomputers have modeled the formation of cosmic structure from initial conditions to the present, allowing predictions to be tested against observations. The combination of data and theory is converging toward a consistent picture, but important uncertainties remain. The depth and extent of the local void are still debated. Different analyses using different methods produce somewhat different results. Some studies suggest a void that extends for 2 billion light years with a 20% density deficit. Others find a smaller or shallower underdensity. The discrepancies reflect the difficulty of measuring something as subtle as a deficit in matter density over cosmic scales. What we can say with confidence is that our local environment is not perfectly average. The evidence for some degree of underdensity is robust, even if the precise parameters are uncertain. And this underdensity, whatever its exact magnitude, contributes to the peculiarities of our observations. And this brings us to another quiet detail that deserves exploration. The shape of the local void matters, not just its depth. If the underdensity were perfectly spherical, centered on our galaxy, its effects would be uniform in all directions. We would observe the same distortion regardless of where we pointed our telescopes. But if the void has a more complex shape, elongated or asymmetric, its effects would vary with direction. Different parts of the sky would show different degrees of deviation from cosmic averages. Some studies have suggested that the local underdensity may indeed be asymmetric. The galaxy counts in certain directions appear lower than in others. The peculiar velocity field shows variations that could reflect an uneven distribution of the surrounding void. If confirmed, this asymmetry would have implications for how we interpret directional variations in cosmological measurements. This is one of the challenges of living within the structure we are trying to study. We cannot step outside the void to get an objective view of its shape. We are embedded within it, trying to infer its geometry from the inside. It is like trying to determine the shape of a room while standing in the center with the lights off, using only echoes and the faint glow of distant windows. Despite these challenges, the basic picture remains coherent. We appear to live in a region of space where matter is somewhat less densely packed than the cosmic average. This underdensity extends for a substantial fraction of a billion light years and influences both the observed velocities of nearby galaxies and our measurements of cosmic expansion. The exact parameters are still being refined, but the qualitative conclusion is increasingly accepted. Let us drift a bit deeper into this idea. If our galaxy resides in an underdensity, what does this imply for the formation and evolution of the Milky Way itself? Galaxies do not form in isolation. They grow through the accumulation of gas and smaller structures, merging with other galaxies over time, accreting matter from the surrounding medium. The rate at which a galaxy grows depends partly on the availability of material in its environment. In a dense region, material is abundant, mergers are frequent, and galaxies can grow large and massive. In an underdense region, material is scarce, mergers are rare, and growth is slower. This suggests that the Milky Way may have experienced a somewhat quieter evolutionary history than galaxies in denser environments. It may have undergone fewer major mergers, accumulated matter more gradually, and developed in relative isolation compared to galaxies in crowded clusters. There is evidence that this may indeed be the case. The Milky Way's disk is remarkably thin and well-ordered, suggesting that it has not been severely disrupted by recent major mergers. Major mergers tend to thicken and disorder galactic disks, leaving behind puffy, chaotic stellar distributions. The fact that our disk remains thin implies that any recent mergers were relatively minor. Additionally, the Milky Way's stellar halo, the sparse cloud of old stars surrounding the disk, contains debris from past accretion events. By analyzing the orbits and compositions of these halo stars, astronomers can reconstruct the merging history of our galaxy. The evidence suggests that the Milky Way has absorbed several smaller galaxies over its lifetime, but has not experienced a truly major merger in many billions of years. This relatively peaceful history is consistent with residing in an underdense environment where encounters are less frequent and more gradual. Whether the local void directly caused this history or merely coincided with it is difficult to determine, but the connection is suggestive. And this brings us to another quiet detail that connects our local environment to the broader story of cosmic evolution. The cosmic web is not merely a static pattern. It is a snapshot of an ongoing process, frozen in time by the finite speed of light. As we look farther into the universe, we look further back in time. The light from a galaxy, 1 billion light years away, left that galaxy 1 billion years ago. What we see is not the universe as it is now, but as it was when each photon began its journey. This means that when we study the cosmic web, we are also studying its evolution. Nearby structures show us the present state. Distant structures show us earlier epochs. By comparing the web at different distances, we can trace how it has changed over billions of years, how voids have grown, how filaments have sharpened, how matter has flowed from low-density regions to high-density ones. The evolution of voids follows a predictable pattern. In the early universe, voids were smaller and shallower, reflecting the modest amplitude of the primordial density fluctuations. Over time, as gravity amplified the differences between dense and underdense regions, voids expanded and deepened. The contrast between the emptiest voids and the densest clusters increased. This process continues today. The local void around our galaxy is not static. It is slowly expanding, its boundaries advancing as matter drains toward the surrounding filaments. The galaxies within it, including the Milky Way, are participating in this expansion, moving apart from one another at rates influenced by both the universal expansion of space and the local gravitational environment. Predicting the future evolution of the local void requires modeling the interaction between gravity and dark energy over cosmic timescales. Dark energy, the mysterious force driving the acceleration of cosmic expansion, dominates the energy budget of the universe and will play an increasingly important role as the cosmos continues to evolve. In the far future, dark energy will cause the expansion to accelerate beyond the gravitational binding of most structures. Galaxies that are not already part of gravitationally bound groups will drift apart, their light redshifting beyond detectability. Voids will merge and grow, eventually dominating the observable universe. But this future is billions of years away. For now, we inhabit a universe where structure is still well-defined, where the cosmic web still traces the flow of matter, and where the local void remains just one cell among countless others in the vast cosmic tapestry. And this brings us to another quiet detail that connects our local environment to the largest scales of the universe. The cosmic microwave background is not perfectly uniform. It contains tiny fluctuations, variations in temperature and polarization that encode information about the early universe. These fluctuations are the seeds from which all cosmic structure grew. By studying their statistical properties, cosmologists can determine the initial conditions that shaped the cosmos. But the fluctuations are not purely primordial. As the microwave background light traveled towards us over the past 13.8 billion years, it passed through the evolving structures of the cosmic web. These structures imprinted additional signals onto the light, secondary effects that overlay the primary primordial fluctuations. One such effect involves the gravitational influence of voids and clusters along the line of sight. As photons enter a void, they gain energy from the gravitational potential. As they exit, they lose energy. If the void were static, these gains and losses would cancel exactly. But the universe is expanding, and as the photon traverses the void expands slightly, making the gravitational potential shallower by the time the photon exits. The net effect is that the photon gains a small amount of energy, appearing slightly warmer than expected. Wait, that seems backward. Let me reconsider. Actually, in an expanding universe dominated by dark energy, the effect works differently. As a photon enters a void, it falls into the gravitational well, gaining energy and blue shifting. As it exits, it climbs out of the well, losing energy and red shifting. In a static universe, these effects would cancel. But in an accelerating universe, the void expands while the photon is inside, making the well shallower by the time the photon exits. The photon loses less energy exiting than it gained entering, so it ends up slightly blue shifted, or equivalently, slightly warmer. Actually, let me think about this more carefully. The integrated Sachs-Wolf effect in its late-time version works as follows. In a universe where expansion is accelerating due to dark energy, gravitational potentials decay over time. As a photon passes through a gravitational well, the well becomes shallower while the photon is traversing it. The photon gains energy falling in and loses energy climbing out. But since the well is shallower when it exits, it loses less energy than it gained. The net result is a slight blue shift, which translates to a slightly higher temperature. For voids, the situation is reversed. A void is a gravitational hill rather than a well. Photons lose energy entering a void and gain energy exiting. If the void is expanding and becoming less underdense over time, actually, let me think again. In the presence of dark energy, the density contrast of voids decreases over time. The void effectively becomes shallower as a gravitational feature. A photon entering the void loses energy climbing the potential hill. As it traverses the void, dark energy causes the potential to flatten. When the photon exits, it gains less energy than it lost entering, because the hill is now less steep. The net result is that photons passing through voids end up slightly cooler than they would otherwise be. This is consistent with observations of cold spots in the microwave background that correlate with the positions of known voids. The largest such cold spot, in the constellation Eridanus, corresponds to the location of a supervoid discovered through galaxy surveys. The correlation between cold spots and voids supports the late-time integrated Sachs-Wolf effect as a real contributor to microwave background anisotropies. For our purposes, this effect provides another window into the structure of the cosmic web. By examining the temperature variations in the microwave background and correlating them with known structures, astronomers can test models of how matter is distributed and how gravitational potentials have evolved. This cross-correlation between maps of the microwave background and maps of galaxy positions has confirmed the reality of dark energy and the validity of the standard cosmological model. If the local void around our galaxy is particularly large or deep, it might contribute a measurable signal to the microwave background in certain directions. Searches for such a signal are ongoing, though the results so far are ambiguous. The expected effect is subtle, and distinguishing it from other sources of temperature variation is challenging. And this brings us to another quiet detail that deserves attention. The cosmic web is not the only large-scale pattern in the universe. There is also the flow of galaxies through the web, the bulk motion of matter responding to gravitational gradients. This flow is coherent over vast distances, with entire regions of space moving together in directions determined by the distribution of surrounding mass. Our local region participates in one such flow. The Milky Way, along with its neighbor galaxies, is moving toward a direction in the sky called the apex of motion. This motion is partly due to attraction toward distant mass concentrations and partly due to repulsion from nearby voids. The combined effect produces a net velocity of several hundred kilometers per second, relative to the cosmic microwave background. This motion was first detected in the 1970s and has since been measured with increasing precision. The direction and magnitude of our motion encode information about the large-scale distribution of matter, including both the visible galaxies and the invisible dark matter that dominates the mass budget. By analyzing the flow of galaxies over progressively larger volumes, astronomers can map the gravitational field of the cosmos. Regions where galaxies are converging indicate overdensities. Regions where they are diverging indicate underdensities. The flow patterns match the predictions of cosmological simulations, providing confidence that our models of structure formation are on the right track. Within this flow, the local void plays a measurable role. It contributes a component of motion away from its center, superimposed on the attraction toward distant masses. The interplay between these opposing influences shapes the trajectory of our galaxy through the cosmic web. How could this be possible? That we can detect the gravitational influence of invisible voids and clusters from motions measured in nearby galaxies. It is possible because gravity is a long-range force. Unlike the short-range forces that hold atoms together, gravity reaches across unlimited distances, though its strength diminishes with the square of the distance. A concentration of mass 100 million light-years away still exerts a measurable pull on our galaxy. And by carefully measuring the velocities of thousands of galaxies, astronomers can infer the presence and location of these distant masses. This is one of the most remarkable achievements of observational cosmology. From our single vantage point in the Milky Way, we can reconstruct the three-dimensional distribution of matter over billions of light-years, not by seeing the matter directly, but by reading its gravitational influence in the motions of galaxies. The technique is analogous to inferring the presence of mountains and valleys by observing the flow of water across a landscape. Where the water converges, there must be a depression. Where it diverges, there must be a rise. And the flow of galaxies tells us that we are in a relative depression, a region of lower than average matter density, where gravitational attraction is weaker and the cosmic expansion is less impeded. Let us drift a bit deeper into this idea. The measurement of peculiar velocities is one of the most powerful tools for probing the large-scale structure of the universe. Unlike galaxy counts, which depend on accurately measuring distances to each galaxy, peculiar velocity measurements can reveal the mass distribution independently of the visible light. The technique relies on a relationship known as the Tully-Fisher relation for spiral galaxies and the fundamental plane for elliptical galaxies. These relationships connect the intrinsic brightness of a galaxy to measurable properties like rotation speed or velocity dispersion. By measuring these properties, astronomers can estimate the intrinsic brightness and thus the distance. Comparing this distance-based estimate to the velocity inferred from redshift reveals the peculiar velocity. Compilations of peculiar velocity measurements for thousands of galaxies have produced maps of the gravitational field over substantial fractions of the observable universe. These maps confirm the web-like structure of the cosmos, with converging flows toward massive clusters and diverging flows away from voids. The local void around our galaxy appears in these maps as a region of diverging flow. Galaxies in our neighborhood are moving away from a common center, pushed by the gravitational influence of denser regions beyond the void's boundaries. The pattern is consistent across different analyses and different data sets, lending confidence to the reality of the underdensity. One intriguing aspect of these measurements is the scale over which the flow persists. Early studies found bulk flows extending to a few hundred million light-years, consistent with expectations from standard cosmology. But more recent analyses have suggested that coherent flows might extend to even larger scales, perhaps 500 million light-years or more. If confirmed, such large-scale flows would pose challenges for the standard cosmological model, which predicts that the universe should be nearly homogeneous on these scales. The presence of coherent flows would imply gravitational gradients, which would require significant inhomogeneities in the matter distribution. This is another area where the interpretation of data remains contested. Different research groups using different methodologies have reached different conclusions about the amplitude and extent of bulk flows. Some find flows consistent with standard predictions. Others find anomalously large flows that suggest an unexpected degree of inhomogeneity. The local void is one piece of this puzzle. If our neighborhood is particularly underdense, it could contribute to larger than expected flows. But whether the local void alone can explain the observations or whether additional structures are needed remains uncertain. And this brings us to another quiet detail that connects our local environment to the fundamental physics of gravity. The standard model of cosmology is built on Einstein's theory of general relativity, the modern theory of gravity. General relativity has been tested with extraordinary precision in the solar system and in observations of binary pulsars. It correctly predicts the bending of light by massive objects, the precession of planetary orbits, and the propagation of gravitational waves. But general relativity has been tested primarily in environments of relatively high density, near stars, planets, and compact objects, in the vast emptiness of cosmic voids, where matter is scarce and gravitational fields are weak. The predictions of general relativity have been less thoroughly tested. Some physicists have proposed modified theories of gravity that behave like general relativity in dense environments but differ in low-density regions. These theories are motivated partly by the desire to explain dark matter and dark energy as manifestations of modified gravity rather than exotic substances. If gravity behaves differently in voids, it could affect the dynamics of galaxies and the evolution of cosmic structure. Testing such theories requires comparing their predictions to observations of void environments. The local void around our galaxy provides one laboratory for such tests. If the dynamics of galaxies within the void deviate from general relativity's predictions in specific ways, it could provide evidence for modified gravity. So far, no definitive deviations have been found. The behavior of galaxies in our local neighborhood is consistent with general relativity, given the uncertainties in the measurements. But the search continues, and improvements in data quality may yet reveal subtle departures from the standard theory. And this brings us to another quiet detail that connects our local environment to the broader question of cosmic structure. The existence of the local void is not surprising in itself. Voids are a natural consequence of gravitational evolution. Any realistic model of cosmic structure formation will produce voids as counterparts to the dense clusters and filaments. What is potentially surprising is the size and depth of the local void, which some analyses suggest is unusually large for a region that just happens to contain our galaxy. If the local void is truly exceptional, if it represents a statistical outlier among the voids of the universe, then our position within it would be correspondingly unusual. We would be living in a rare environment, one that could not be expected to occur frequently if one sampled random locations in the cosmos. This raises questions about the cosmological principle and about how we should interpret our observations. If our location is unusual, can we trust that our measurements reflect cosmic averages? Are we seeing the universe as it truly is, or are we seeing a distorted version filtered through an atypical local environment? The answer, ultimately, depends on how unusual the local void really is. Estimates of its rarity vary. Some studies suggest that voids of this size and depth should occur with some frequency in a universe governed by standard physics. Others find that such voids are exceedingly rare, pushing the boundaries of what standard cosmology allows. The discrepancy between different estimates reflects both observational uncertainties and differences in methodology. Defining the boundaries of a void is not straightforward. The transition from underdense to average density is gradual, and different criteria produce different size estimates. Similarly, measuring the density contrast depends on how one counts galaxies and how one accounts for observational selection effects. As surveys improve and analysis methods are refined, the properties of the local void will become better constrained. Future telescopes will map the galaxy distribution to greater depths and with higher precision, allowing more accurate determinations of where the void ends and normal density space begins. And this brings us to another quiet detail that deserves attention. The local void is not the only large structure in our cosmic neighborhood. We are also associated with a concentration of matter known as a supercluster, a sprawling collection of galaxy groups and clusters that spans hundreds of millions of light years. This supercluster, sometimes called Laniakea, is defined not by a physical boundary, but by a dynamical one. It encompasses all the galaxies whose motion is directed inward toward a common center of gravity. Beyond the edges of Laniakea, galaxies are flowing away, drawn toward other superclusters or their own centers of attraction. The identification of Laniakea was achieved by mapping the peculiar velocities of thousands of galaxies and tracing the flow lines of motion. Where the flow converges, mass is concentrated. Where it diverges, voids intervene. The boundaries of superclusters are the surfaces where the flow changes from converging to diverging, the cosmic watersheds that separate one basin of attraction from another. Our galaxy lies near the edge of Laniakea, far from its center. The center is occupied by a massive complex of galaxy clusters that exerts a gravitational pull felt across the entire supercluster. We are moving toward this center, along with all the other galaxies in Laniakea, though the motion is slow and will take billions of years to cover any significant distance. But here is the interesting part. Laniakea itself is embedded within the local void. The supercluster, with all its tens of thousands of galaxies, is still underdense compared to the cosmic average when averaged over its full volume. The dense clusters at its center are balanced by the vast empty spaces between them. The net density is below average, making Laniakea part of the local underdensity rather than a contradiction of it. This nested structure, a supercluster within a void, illustrates the hierarchical nature of the cosmic web. Density contrasts exist on every scale. Small voids sit between galaxy groups. Larger voids separate superclusters. Still larger underdensities may extend across billions of light years. At each level, the same principles apply. Gravity pulls matter toward dense regions and leaves voids behind. And this brings us to another quiet detail that connects our local environment to the observable universe as a whole. The observable universe is the portion of the cosmos from which light has had time to reach us since the Big Bang. Its edge, the cosmological horizon, marks the distance beyond which photons have not had enough time to make the journey. This horizon is not a physical barrier, but a limitation of observation, a boundary set by the finite speed of light and the finite age of the universe. The observable universe contains approximately 2 trillion galaxies, give or take, distributed across the cosmic web. These galaxies cluster into groups, which cluster into clusters, which align into filaments, which intersect at massive nodes. The pattern is self-similar across a range of scales, though ultimately it becomes homogeneous when averaged over distances of a few 100 million light years or more. Homogeneity, in this context, means that the average properties of the universe, the density of matter, the expansion rate, The temperature of the cosmic background are the same regardless of location when measured over sufficiently large regions. Local variations exist, but they average out when you zoom out far enough. The local void represents one such local variation. It is significant on scales of hundreds of millions of light years, but becomes increasingly irrelevant when averaged over billions of light years. From the perspective of the entire observable universe, our underdense neighborhood is a minor fluctuation, one cell among countless cells in the cosmic web. But from our perspective, living inside that cell, the fluctuation matters. It colors our observations, influences our measurements, and challenges our assumptions about what is typical and what is anomalous. And this brings us to another quiet detail that connects our local environment to the deepest questions in cosmology. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, has been one of the guiding principles of modern cosmology. It simplifies the mathematics, allows tractable models, and seems consistent with observations when viewed with appropriate coarse graining. But the principle is an assumption, not a proven law. It could be violated. The universe could have large-scale structure that persists beyond the scales where homogeneity is expected. Some observations have hinted at such violations, including the apparent alignment of structures across billions of light years and the existence of unusually large voids or concentrations. If the local void is part of a larger pattern of inhomogeneity, if the cosmic web has structure on scales larger than currently recognized, the implications would be profound. It could affect our understanding of dark energy, dark matter, and the overall geometry of the universe. For now, the evidence remains ambiguous. The local void is real, but whether it represents the tip of a larger iceberg of inhomogeneity or merely a typical fluctuation in an otherwise homogeneous cosmos is not yet clear. Future surveys, probing the universe to greater depths and with greater precision, will help answer this question. And this brings us to another quiet detail that deserves our attention. The cosmic microwave background provides the most powerful test of cosmological homogeneity. This ancient light was released when the universe was nearly uniform, and its patterns of temperature fluctuations reflects the primordial seeds of structure. By analyzing the statistical properties of these fluctuations, cosmologists can test whether the universe obeys the expected patterns of homogeneity and isotropy. So far, the results are largely consistent with expectations. The fluctuations show the predicted correlations on various angular scales. The universe appears to be statistically homogeneous and isotropic to a high degree, with the caveat that our observations are limited to the region accessible to our telescopes. But there are hints of anomalies. Some patterns in the microwave background appear unexpectedly aligned with the geometry of the solar system or the plane of the galaxy. Others show slight asymmetries between opposite hemispheres of the sky. These anomalies are statistically marginal, and their interpretation is debated. They could be fluctuations, instrumental artifacts, or hints of genuine departures from the cosmological principle. The local void adds another layer of complexity. If our vantage point is unusual, it could affect our perception of the microwave background in subtle ways. Correcting for local effects is essential for extracting the primordial signal, but it requires knowing our local environment with precision. And this brings us to another quiet detail. that connects our local environment to the nature of observation itself. Everything we know about the universe beyond our planet comes from photons. These particles of light carry information from distant sources to our telescopes, where we decode their wavelengths, their intensities, their polarizations. The information is rich but filtered, shaped by the medium through which the photons have traveled. Living within a void affects this medium. It changes the gravitational potentials the photons traverse. It alters the distribution of galaxies and gas that the photons encounter. It influences the peculiar velocities that shift the wavelengths of nearby sources. All of these effects layer onto the intrinsic properties of the sources, creating a composite signal that must be carefully disentangled. This is the challenge of observational cosmology. We are not passive observers viewing the cosmos from outside. We are embedded within it, participating in its dynamics, affected by its structures. Our observations are necessarily partial, filtered, perspectival. Extracting universal truths requires acknowledging and correcting for our particular position. The recognition that we live in a void is a step towards such correction. It acknowledges that our local environment is not a featureless vacuum, but a structured region with measurable properties. By characterizing those properties, we can better understand how they affect our observations and adjust our conclusions accordingly. And this brings us to another quiet detail that deserves exploration. The galaxies within the local void are not uniformly distributed. They cluster into groups and filaments on smaller scales, even within the broader underdensity. The cosmic web has structure at every level, from the largest superclusters to the smallest galaxy pairs. The void is underdense on average, but it contains local concentrations that exceed the average density. Our own local group, the collection of galaxies that includes the Milky Way and its neighbors, is one such concentration. It contains roughly 80 galaxies, though the exact count depends on how you define a galaxy. The largest members are the Milky Way and Andromeda, both spiral galaxies of significant mass. The rest are smaller, mostly dwarf galaxies that orbit the larger ones, or drift through the local group's common gravitational field. The local group is gravitationally bound, meaning its members will remain associated indefinitely. The cosmic expansion does not affect systems that are bound by gravity. The Milky Way and Andromeda, for instance, are actually approaching each other, drawn together by their mutual gravity. In a few billion years, they will merge into a single, larger galaxy. This merger will be the most significant event in the local group's future, at least in the near term. But it will occur within the broader context of the local void. The merged galaxy will continue to reside in an underdense environment, its long-term fate shaped by the surrounding emptiness. And this brings us to another quiet detail that connects our local environment to the evolution of structure. Galaxies in underdense environments evolve differently from galaxies in dense environments. The difference arises because galaxy evolution is influenced by interactions with neighbors. In dense regions, galaxies frequently encounter one another. They merge, strip gas from each other, trigger bursts of star formation, and transform their structures. In underdense regions, encounters are rare. Galaxies evolve in relative isolation, retaining their gas and forming stars at a slower, steadier pace. This environmental dependence has been confirmed through observations of galaxies in different settings. Void galaxies tend to be bluer, indicating ongoing star formation. Cluster galaxies tend to be redder, indicating older stellar populations and little recent star formation. The dichotomy reflects the different evolutionary pathways available in different environments. The Milky Way, residing on the edge of a local group within a local void, occupies an intermediate position. It has experienced some interactions, including minor mergers and the ongoing accretion of dwarf satellites. But it has avoided the major disruptions that transform galaxies in dense clusters. Its disk has remained intact, its star formation has continued, and its structure has evolved gradually over billions of years. Whether this relatively peaceful history is typical for galaxies at our location in the cosmic web, or somewhat unusual, is not entirely clear. The statistics of galaxy evolution are complex, and disentangling the effects of local environment from other factors like galaxy mass and formation history is challenging. And this brings us to another quiet detail that deserves attention. The future evolution of the local void will be shaped by the interplay between gravity and dark energy. Gravity pulls matter toward dense regions, opposing the expansion of voids. Dark energy accelerates the expansion of space, encouraging voids to grow. The outcome depends on which force dominates. In the current cosmic epoch, dark energy has become the dominant component of the universe's energy budget. Its influence grows stronger as space expands, while the influence of matter diminishes as it becomes more diluted. This trend will continue and accelerate in the future. For voids, this means continued expansion. The local void will grow larger and emptier over cosmic time. Its boundaries will advance, pushing into the surrounding filaments. The galaxies within it will drift farther apart, carried by the expanding space between them. Eventually, on timescales of tens of billions of years, the expansion will isolate local groups of galaxies from one another. Galaxies that are not gravitationally bound together will recede beyond each other's cosmological horizons. The observable universe, as seen from any given galaxy, will shrink to include only the nearby gravitationally bound system. For the Milky Way and its neighbors in the local group, this future is billions of years away. Our immediate descendants, if any exist, will continue to see a rich sky filled with billions of observable galaxies. But in the far future, this richness will fade. The galaxies will redshift beyond visibility, leaving only the local group and the merged remnant of the Milky Way and Andromeda against a dark, empty sky. This far future scenario is a consequence of dark energy and accelerating expansion. It is not specific to our location in the local void. All galaxies, regardless of their environment, will eventually face the same isolation. But galaxies and voids will reach this state somewhat sooner, having always inhabited less crowded regions. And this brings us to another quiet detail that connects our local environment to the nature of cosmic time. The universe has not always looked the way it does today. In its earliest epochs, space was filled with a nearly uniform plasma, too hot and dense for atoms to form. Photons bounced endlessly between charged particles, and the cosmos was opaque. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. Photons could finally travel freely, and the cosmos became transparent. The light released at this transition, now stretched by cosmic expansion into microwave wavelengths, is the cosmic microwave background we observe today. Since that time, the universe has evolved from a smooth plasma to the web of galaxies and voids we see today. The first stars formed a few 100 million years after the Big Bang, igniting the cosmic dark ages with their light. Galaxies assembled over billions of years, growing through accretion and mergers. The cosmic web emerged as gravity shaped the initial fluctuations into the filaments and voids we observe. The local void around our galaxy is a product of this billions-year evolution. It began as a slightly underdense fluctuation in the primordial plasma, a region where the density was marginally below average. Over time, this minor deficit was amplified by gravity. Matter flowed out toward denser surroundings, and the void grew. By the time the Milky Way formed, roughly 10 billion years ago, the local void was already a significant feature. Our galaxy emerged in this underdense environment and has remained there ever since, participating in the void's ongoing expansion. And this brings us to another quiet detail that deserves exploration. The primordial fluctuations that seeded the cosmic web are believed to have originated during inflation, a hypothetical epoch of exponential expansion in the universe's first fraction of a second. During inflation, quantum fluctuations were stretched to cosmological scales, imprinting a pattern of density variations that would later grow into galaxies and voids. The statistical properties of these fluctuations are remarkably well constrained by observations of the cosmic microwave background. They are nearly Gaussian, meaning their distribution follows the familiar bell curve. They are nearly scale invariant, meaning fluctuations of different sizes have similar amplitudes. They are correlated in ways that match the predictions of inflationary models. These properties provide the initial conditions for structure formation. Cosmological simulations begin with a distribution of fluctuations that matches the observed properties, and then evolve the universe forward under the influence of gravity and dark energy. The simulations produce cosmic webs that resemble the observed web, with filaments, clusters, and voids in the expected proportions. The existence of the local void is consistent with these simulations. Voids of various sizes arise naturally from the initial conditions. The question of whether our particular void is unusually large or deep is a statistical question that can be addressed by comparing observations to simulations. Current comparisons suggest that the local void may be somewhat unusual, but not impossibly so. It lies toward the extreme end of the expected distribution, a region of low probability, but not zero probability. We may simply have drawn an unlucky hand from the cosmic deck, finding ourselves in an environment that is rare, but not forbidden. And this brings us to another quiet detail that connects our local environment to the boundaries of knowledge. The universe beyond the cosmological horizon is inaccessible to observation. Photons from those distant regions have not had enough time to reach us, and they never will if the expansion continues to accelerate. We cannot know what lies beyond the horizon, whether the cosmos continues in the same web-like pattern, or whether different structures and rules apply. This limitation is fundamental. No improvement in telescope technology or observational technique can overcome it. We are confined to our visible bubble, making inferences from the portion of the cosmos that has revealed itself to us. The local void affects how we interpret this visible bubble. It alters the photons that reach us, influences the dynamics of nearby galaxies, and shapes the patterns we see in the cosmic microwave background. Correcting for these effects is essential for understanding the universe at large, but the corrections are imperfect. Uncertainties in our knowledge of the local environment propagate into uncertainties in our conclusions about the cosmos. This is not a weakness unique to cosmology. All sciences face the challenge of making inferences from limited data, but cosmology faces it in an especially acute form because we have only one universe to observe and only one vantage point from which to observe it. We cannot repeat the experiment, cannot sample other locations, cannot compare our observations to those of observers elsewhere. What we can do is characterize our local environment as thoroughly as possible, model its effects on our observations, and quantify the resulting uncertainties. This is the work that astronomers and cosmologists are engaged in today. It is slow, painstaking, and fraught with ambiguity. But it is the only path to reliable knowledge about the cosmos. And this brings us to another quiet detail that deserves attention. The measurements that revealed the local void did not come from a single observation or a single team. They emerged from decades of work by thousands of scientists, using telescopes on the ground and in space, analyzing data with increasingly sophisticated methods. The conclusion that we live in an underdensity is not a speculative hypothesis, but an observational result, supported by multiple independent lines of evidence. Galaxy surveys have mapped the distribution of visible matter over progressively larger volumes. Peculiar velocity measurements have traced the gravitational flows driven by that matter. Studies of the cosmic microwave background have probed the structures through which its light has traveled. Each approach has its strengths and limitations, but together they paint a consistent picture. This convergence of evidence is the hallmark of scientific reliability. No single measurement is definitive, but when multiple measurements agree, confidence grows. The existence of the local void has passed this test. It is accepted by most cosmologists as a real feature of our cosmic environment, even if its precise properties remain uncertain. And this brings us to another quiet detail that connects our local environment to the practice of science. Science progresses through conjecture and refutation, through the proposal of hypotheses and their testing against observations. The local void entered scientific discourse as a hypothesis, a possible explanation for certain anomalies in the data. It was tested against additional observations and found to be consistent. It now stands as a provisional conclusion, subject to revision if future data warrant. The Hubble tension, the discrepancy between local and distant measurements of cosmic expansion, provided one of the main motivations for investigating our local environment. If the tension could be explained by the local void, it would resolve a major puzzle without requiring new physics. This is an appealing prospect, because new physics is speculative while local environmental effects are grounded in established gravitational theory. But the question is not yet settled. Some analyses suggest the local void can fully account for the Hubble tension. Others find that the void is not deep or extensive enough to explain the entire discrepancy. The debate continues, with new data and new analyses appearing regularly. What is certain is that our local environment is not irrelevant. Whether or not it fully explains the Hubble tension, it contributes to the dynamics of nearby galaxies and affects our measurements of the cosmos. Ignoring it would be a mistake. Any complete account of our observations must include the local void as one of the factors shaping what we see. And this brings us to another quiet detail that deserves exploration. The concept of a void is deceptively simple. It sounds like empty space, a region containing nothing. But cosmic voids are not truly empty. They contain galaxies, gas, dark matter, and dark energy, just in lower concentrations than average. The term void refers to a relative underdensity, not an absolute absence. This distinction matters because voids are not passive features. They are dynamic regions where physics operates in a different regime. The weakness of gravity, the dominance of dark energy, the scarcity of interactions, all these factors shape the behavior of matter within voids. Understanding voids requires understanding how the same physical laws play out in different density environments. Galaxies and voids provide laboratories for studying these effects. They are isolated, undisturbed, and slowly evolving. By comparing them to galaxies in dense environments, astronomers can disentangle the effects of nature and nurture, the intrinsic properties of galaxies, and the environmental influences that shape them. The Milky Way, though not deeply embedded in the local void, participates in this experiment. Our galaxy's structure and history carry information about our environment. By studying the Milky Way in the context of the local void, we can learn about both. And this brings us to another quiet detail that connects our local environment to the detection of gravitational waves. Gravitational waves are ripples in space-time produced by accelerating masses. They were predicted by Einstein a century ago and first detected in 2015 by the LIGO observatories. Since then, dozens of gravitational wave events have been observed, mostly from merging black holes and neutron stars. The detection of gravitational waves opened a new window on the universe. These waves carry information about extreme events in distant galaxies, information that is not accessible through light. They provide independent measurements of cosmic distances, complementing the traditional methods based on supernovae and other standard candles. Gravitational wave measurements of the Hubble constant are still in their infancy, but they hold promise for resolving the Hubble tension. If gravitational waves can provide an independent determination of the expansion rate, unaffected by the peculiarities of our local environment, they could reveal whether the tension is real or an artifact of our position in the void. This is one of the exciting frontiers of contemporary cosmology. New detectors are being planned and constructed, with sensitivities far exceeding current capabilities. In the coming decades, gravitational wave observations will become a standard tool for cosmological measurement, potentially transforming our understanding of cosmic expansion. And this brings us to another quiet detail that deserves attention. The local void is not the only anomaly in our cosmic neighborhood. Several other features have been noted that, taken together, suggest our region of space may be somewhat unusual. One such feature is the motion of the local group. Our galaxy and its neighbors are moving relative to the cosmic microwave background at a velocity of about 600 kilometers per second. This motion is larger than expected from the distribution of visible matter alone, suggesting the presence of hidden mass concentrations or voids that influence our trajectory. Another feature is the apparent alignment of the motion with certain asymmetries in the microwave background. The temperature of the background is slightly higher in one hemisphere of the sky than the other, and this asymmetry aligns suspiciously with the direction of our motion. Whether this alignment is a coincidence, a statistical fluke, or a hint of deeper structure remains debated. A third feature is the existence of particularly empty regions in certain directions, void spaces that appear even emptier than the general local underdensity. These supervoids may contribute to temperature anomalies in the microwave background and may affect the dynamics of nearby galaxies in measurable ways. Each of these features, considered alone, might be dismissed as a rare but unremarkable fluctuation. Taken together, they paint a picture of a cosmic environment that is more complex and perhaps more unusual than standard models would predict. Whether this complexity reflects real, large-scale inhomogeneity or merely the limitations of our current understanding is an open question. And this brings us to another quiet detail that connects our local environment to the nature of dark energy. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. It makes up roughly 68% of the total energy content of the cosmos, dominating over both ordinary matter and dark matter. Despite its preponderance, its nature remains almost completely unknown. The simplest model of dark energy is a cosmological constant, a fixed energy density inherent to space itself. This model, proposed by Einstein and later revived to explain observations, requires no new physics beyond a general relativity. It is consistent with all observations to date, though it raises theoretical puzzles about why the energy density has the particular value it does. Alternative models propose that dark energy is dynamical, varying in strength over time or space. These models introduce new fields or modifications to gravity that produce accelerating expansion. They are more complex than the cosmological constant, but could explain certain observations that the constant cannot. One way to distinguish between these models is to measure how dark energy behaves in different environments. If dark energy is truly constant, its effects should be the same in voids as in clusters. If it is dynamical, there might be subtle differences that observations could detect. The local void provides one environment for such tests. By measuring the expansion rate within the void and comparing it to the rate in denser regions, astronomers can constrain whether dark energy has any environmental dependence. So far, no such dependence has been detected, but the measurements are challenging and the constraints are not yet tight. And this brings us to another quiet detail that deserves exploration. The relationship between the local void and the Hubble tension illustrates a broader challenge in cosmology, the challenge of interpreting observations that are influenced by unknown factors. The Hubble tension could be explained by the local void, or by new physics, or by some combination of both. Distinguishing between these possibilities requires understanding the local environment better than we currently do. It requires ruling out environmental effects before concluding that new physics is needed, or quantifying those effects precisely enough to measure the residual tension. This is the essence of the scientific method applied to cosmology. We do not have direct access to the truth. We have only observations, which are filtered through our local environment and processed by our instruments. Extracting the underlying reality requires peeling back these layers, accounting for every known effect, and remaining open to the possibility that unknown effects remain. The local void is one such effect, now known but not yet fully characterized. Its discovery has changed how cosmologists approach the Hubble tension and other measurements. It has introduced a new variable that must be considered in any analysis of local observations. And this brings us to another quiet detail that connects our local environment to the architecture of the cosmos. The cosmic web is often described using analogies to familiar structures: a foam, a sponge, a network of roads and intersections. These analogies capture aspects of the web's topology, but can also mislead. The web is not a physical object with fixed boundaries and defined surfaces. It is a pattern of density, a distribution of matter that grades continuously from high to low. Voids are regions where the density is low, but there is no sharp edge where a void ends and a filament begins. Instead, the density rises gradually as you move from the center of a void toward the surrounding structures. The transition is smooth, making it challenging to define where one region ends and another begins. Different definitions produce different maps. Some analyses define voids as regions enclosed by surfaces of a certain density threshold. Others define them by the flow of matter, identifying voids as regions from which matter is flowing outward. Still others use the shapes of density contours to identify distinct structural features. These different definitions can yield different sizes and shapes for the same void. They can even produce different counts of how many voids exist in a given volume of space. The local void is subject to these ambiguities like any other void. Its extent depends partly on how you define its boundaries. This is not a flaw in the science, but a reflection of the underlying complexity. The cosmic web is a continuous structure, and dividing it into discrete features involves choices that affect the results. Understanding the local void requires being explicit about these choices and recognizing how they influence conclusions. And this brings us to another quiet detail that deserves attention. The discovery that we live in a void was not a sudden revelation, but a gradual accumulation of evidence. Early hints appeared in galaxy surveys of the 1980s and 1990s, which showed that the immediate neighborhood of the Milky Way was somewhat less densely populated than regions farther away. But these early surveys covered only small volumes and were subject to significant uncertainties. As surveys grew larger and more complete, the evidence strengthened. The Sloan Digital Sky Survey, which began observations in 2000 and continues today, has mapped millions of galaxies over a significant fraction of the sky. Its data have been used to characterize the local density environment with unprecedented precision. Other surveys have contributed complementary data. The 2-micron all-sky survey observed in infrared wavelengths penetrating the dust that obscures parts of the sky in visible light. The WISE satellite extended infrared coverage to fainter sources. The Gaia satellite measured precise distances to billions of stars in the Milky Way, enabling more accurate mapping of local structures. Together, these surveys have built a detailed picture of our cosmic neighborhood. The local void is a robust feature of this picture, appearing in analyses that use different data sets and different methods. Its existence is not in doubt, even if its precise parameters remain uncertain. And this brings us to another quiet detail that connects our local environment to the practical challenges of observation. Observing the cosmic web is more difficult in some directions than others. The plane of the Milky Way, dense with stars and dust, blocks our view of extragalactic objects. This zone of avoidance, as it is called, runs across the sky like a band, making it impossible to see the galaxies behind it. Cosmological analyses must account for this missing data. They can interpolate across the zone, using the observed structure on either side to infer what lies behind. They can also use wavelengths that penetrate dust better, like infrared and radio. But some information is inevitably lost. The zone of avoidance runs through part of the local void, obscuring structures that would otherwise be visible. This limitation affects our understanding of the void's shape and extent. In certain directions, we have detailed maps of the galaxy distribution. In others, we have only estimates based on indirect evidence. Future surveys using radio telescopes and infrared satellites will partially fill these gaps. But the zone of avoidance will remain a challenge as long as we observe from within the Milky Way. It is another reminder that our perspective is limited, shaped by the accident of our location. And this brings us to another quiet detail that deserves exploration. The local void is not an isolated phenomenon. Similar underdensities exist throughout the cosmos, each with its own size, shape, and depth. Some are much larger than the local void. Others are smaller, but deeper. The distribution of void properties provides constraints on cosmological models, which must reproduce this distribution through simulations. Comparisons between simulated and observed voids have generally been encouraging. The range of void sizes and depths in simulations matches observations reasonably well. The relationship between voids and the surrounding structures also matches. This agreement supports the standard cosmological model and the initial conditions derived from the cosmic microwave background. But there are tensions. Some observed voids appear larger or deeper than simulations easily produce. The local void may be one example, though this is debated. If such extreme voids are genuinely more common than simulations predict, it could indicate that the initial conditions were different than assumed, or that gravity operates differently than expected, or that dark energy has properties not captured in current models. Resolving these tensions requires better observations and better simulations. Surveys must characterize void properties more precisely, with careful attention to systematic errors. Simulations must model larger volumes with higher resolution, capturing the full range of cosmic structures. The work is ongoing and will continue for years to come. And this brings us to another quiet detail that connects our local environment to the search for understanding. Cosmology is, in some sense, a pursuit of perspective. We seek to understand the universe as a whole, to see beyond our limited vantage point, to construct a picture that transcends our particular location and moment. The discovery that we live in a void is both a challenge to this pursuit and an opportunity for it. The challenge is that our observations may not be representative. The opportunity is that understanding our environment deepens our knowledge of the cosmos. By characterizing the local void, we learn about gravitational dynamics, structure formation, and the behavior of dark energy. We develop techniques that can be applied to distant voids, extending our reach across the universe. There is something poetic about living in a void. It suggests that even in the emptiest regions of the cosmos, complex structures can arise, galaxies can form, and, on at least one planet, beings can emerge who seek to understand their place in the vastness. The void is not barren. It is a different kind of environment, with its own rhythms and its own possibilities. And this brings us to another quiet detail that deserves attention. The study of cosmic structure has implications beyond pure cosmology. It connects to questions about the origins of galaxies, the nature of dark matter, the behavior of gravity on the largest scales. Each of these topics feeds into and out of our understanding of voids in the cosmic web. Dark matter, for example, provides the gravitational scaffolding on which visible structure forms. Its distribution determines where galaxies appear and where voids open. Measuring the properties of voids constrains the properties of dark matter, including its self-interactions and its response to gravity. Similarly, the behavior of gravity can be tested by observing how matter moves within and around voids. Modified gravity theories make different predictions than general relativity for the dynamics of underdense regions. Comparing these predictions to observations constrains which theories are viable. These connections illustrate the holistic nature of cosmological research. No topic exists in isolation. Understanding one aspect of the universe requires understanding many others. The local void is not just a feature of our neighborhood, but a window into fundamental physics. And this brings us to another quiet detail that connects our local environment to the nature of scientific knowledge. What we know about the local void is provisional. It is based on the best available data and the most careful analyses, but it is subject to revision as new data arrive. Future surveys will refine our understanding, perhaps confirming current conclusions, perhaps revealing surprises. This provisionality is a feature of all scientific knowledge. We do not have access to absolute truths, only to the best approximations that our observations and theories can provide. The history of cosmology is filled with revisions, with ideas that seemed secure being overturned or modified as new evidence emerged. The local void is part of this ongoing story. Its existence is well established, but its properties are still being debated. Its implications for the Hubble tension and other puzzles are still being explored. In 10 or 20 years, our understanding may be substantially different from what it is today. This is not a weakness of science, but a strength. It reflects the willingness to follow evidence wherever it leads, to abandon cherished ideas when they fail to match observations, to embrace uncertainty as the price of truth. The local void is one chapter in this ongoing story, a chapter that is still being written. And this brings us to another quiet detail that deserves attention. The realization that we live in a void raises philosophical questions about cosmic significance and location. For centuries, science has progressively displaced humanity from any special position in the cosmos. We are not at the center of the solar system, not at the center of the galaxy, not at the center of the universe. The Copernican principle, as this displacement is sometimes called, has guided scientific thinking toward assumptions of mediocrity, the idea that our position is typical rather than special. Living in a void complicates this narrative. If our environment is unusual, we are not entirely typical observers. We may see the cosmos differently than observers in denser regions. Our measurements may require corrections that observers elsewhere would not need, but this does not make us special in any cosmic sense. Voids are a natural part of the universe, and someone must inhabit them. The galaxies within voids are not privileged, just differently situated. Our position is unusual statistically, but not unique or central. In fact, recognizing our unusual position is a triumph of the scientific method. It shows that we can step outside our immediate perspective, characterize our environment objectively, and account for its effects on our observations. This is the opposite of geocentrism or anthropocentrism. It is an acknowledgement that understanding the universe requires understanding ourselves as part of it. And this brings us to another quiet detail that connects our local environment to the vastness of cosmic time. The local void has existed for billions of years and will persist for billions more. Its evolution is slow, governed by the patient workings of gravity and the inexorable expansion of dark energy. On human timescales, it appears static, unchanging. But on cosmic timescales, it is a dynamic feature, growing and deepening as the universe ages. In the far future, as dark energy continues to accelerate the expansion, the local void will merge with surrounding voids, erasing the distinctions between one underdense region and another. The cosmic web will dissolve, its filaments thinning until only isolated groups of galaxies remain, surrounded by ever-expanding emptiness. This future is inconceivably distant. Trillions of years will pass before the universe reaches such a state. Long before then, the sun will have died, the earth will have been consumed, and any remnants of human civilization will be unrecognizable. The local void's ultimate fate is not our concern in any practical sense, but contemplating this future places our existence in perspective. We live in a particular epoch, a particular environment, within a particular void. These circumstances are contingent, the result of initial conditions we did not choose, and processes we did not direct. And yet, here we are, able to recognize our situation and to marvel at it. And this brings us to another quiet detail that deserves exploration. The discovery of the local void is part of a larger project of cosmic cartography, the mapping of the universe's structure at every scale. From the distribution of atoms in a gas cloud to the filaments spanning billions of light years, the cosmos exhibits structure that reflects the underlying physics. Mapping this structure requires many different tools. Telescopes observing in different wavelengths reveal different components of the cosmic web. Spectroscopy measures the motions of galaxies, revealing the gravitational flows that shape large-scale structure. Numerical simulations model the evolution of the universe, providing predictions that can be compared to observations. The local void emerged from this cartographic effort. It was not discovered by a single observation, but assembled from the contributions of many researchers over many years. Its existence is a collective achievement, a testament to the power of coordinated scientific inquiry. And this brings us to another quiet detail that connects our local environment to the future of cosmological research. The next generation of telescopes and surveys will dramatically expand our view of the universe. The Vera Rubin Observatory will survey the entire southern sky repeatedly, discovering transient phenomena and mapping the galaxy distribution with unprecedented completeness. The Euclid satellite will measure the shapes and positions of billions of galaxies, constraining the properties of dark energy with high precision. The Square Kilometer Array will observe in radio wavelengths, probing neutral hydrogen and the cosmic web at early epochs. These facilities will provide new data on the local void and its surroundings. They will refine measurements of the void's extent and depth. They will trace the gravitational flows that the void produces. They will test whether the Hubble tension can be explained by our local environment, or whether new physics is required. The answers to these questions are not yet known. They depend on what the data reveal, on whether the local void is exactly as we currently believe, or different in surprising ways. The uncertainty is part of the excitement. We stand at the edge of knowledge, looking out at a universe that has not yet finished revealing its secrets. And this brings us to another quiet detail that deserves attention as we near the conclusion of our exploration. Living in a void shapes our view of the universe, but it does not fundamentally alter our relationship to the cosmos. We are still made of the same elements that exist in dense clusters and filaments. We are still governed by the same physical laws. We still participate in the same cosmic evolution that began with the Big Bang and will continue for eons to come. The local void is a context, not a destiny. It influences our observations and challenges our assumptions, but it does not limit what we can learn. By recognizing and accounting for our environment, we can still extract universal truths from local measurements. We can still glimpse the cosmic story of which we are a small but conscious part. And this brings us to another quiet detail that offers a final reflection on our cosmic situation. The universe is vast beyond comprehension, containing billions of galaxies, each with billions of stars. Within this immensity, our galaxy is one among countless others. Our solar system is one among trillions. Our planet is one among a number that may exceed the stars themselves. And yet, here, on this small world, within a local void on the outskirts of a supercluster, embedded in the cosmic web, beings have emerged who can ask questions about the cosmos. We can map the universe, characterize our neighborhood, and wonder about our place in the grand scheme. This is not a contradiction, but a consequence. The universe is large enough, and old enough, and complex enough that such beings can arise. The local void, far from being a barrier to understanding, is part of the story that led to us. Its existence is a reminder that the cosmos is not uniform, but textured, not simple, but structured, not empty, but full of the conditions that make wonder possible. The void is real. Our position within it is measurable, and our capacity to recognize and study it is a remarkable achievement, a testament to the power of human curiosity applied to the mysteries of the cosmos. This journey through the local void has taken us from the measurements of nearby galaxies to the edges of the observable universe, from the ancient light of the cosmic microwave background to the far future dissolution of cosmic structure. We have explored the gravitational flows that reveal hidden mass distributions, the statistical anomalies that challenge our models, and the philosophical implications of occupying an unusual position in the cosmic web. Throughout this exploration, one theme has remained constant. The universe is more intricate than it appears. Its structures are nested within structures. Its patterns emerge from the interplay of gravity and expansion. Its properties depend on the scales at which they are measured. Understanding this intricacy requires patience, precision, and a willingness to question assumptions. The local void is one thread in this tapestry, a feature that reminds us of our particular circumstances, even as we seek universal knowledge. It is not the end of the story, but a chapter in an ongoing investigation, an investigation that will continue as long as there are minds curious enough to ask what lies beyond the next horizon. And so, our exploration draws to a quiet close. The galaxies continue their patient drift through the expanding void. The cosmic web continues its slow evolution. And somewhere within this vast pattern, on a small planet orbiting an ordinary star in an underdense corner of the cosmos, a species wonders at its place in the scheme of things and finds in the wondering a kind of meaning. The universe does not offer easy answers, but it offers endlessly fascinating questions. The local void is one such question, an invitation to look more closely, measure more precisely, and think more deeply about the reality that surrounds us. It is a question that has already yielded remarkable insights and it will continue to reward those who pursue it with patience and care. In the end, we are not diminished by living in a void. We are enriched by the knowledge of where we are and how unusual our cosmic neighborhood may be. This knowledge is a gift, earned through generations of careful observation and creative analysis. It connects us to the cosmos in a profound way, reminding us that we are not separate from the universe, but intimately part of it, products of its processes, inhabitants of its structures, observers of its grandeur. The void continues to expand. The web continues to evolve. And the questions continue to multiply, each answer revealing new puzzles, each discovery opening new horizons. This is the nature of cosmological inquiry, an endless journey through the infinite reaches of space and the even more vast expanses of the unknown. And as we contemplate this journey, we can find a certain peace in the recognition that understanding is a process, not a destination. The local void will still be here tomorrow, and the day after, and for billions of years to come. Our understanding of it will deepen incrementally through the patient accumulation of data and the careful refinement of theory. The mystery will persist even as we illuminate it, for the cosmos always has more to reveal. This is the story of the local void, told not as a sequence of facts, but as a journey through ideas. It is a story about structure and emptiness, about measurement and interpretation, about our place in a universe that is both simpler and more complex than we ever imagined. It is a story that will continue to unfold, carrying us toward ever deeper understanding of the cosmos we call home. The silence between galaxies is not truly silent. It speaks in the language of gravity, in the patterns of motion, in the subtle imprints on ancient light. Learning to read this language is the work of generations, a labor that connects us to everyone who has ever looked up at the night sky and wondered what lies beyond. We are part of that ancient tradition, inheritors of that profound curiosity, and the local void is one of the mysteries we have been given to explore. And so the exploration continues into the quiet depths of cosmic emptiness, toward an understanding that is always just beyond our reach, but always worth pursuing. The void awaits, and with it, all the questions we have yet to ask, and all the answers we have yet to find. This is the universe we inhabit. This is the void we call home. And yet, there is more to explore, more details that deserve our attention as we consider the implications of our cosmic situation. The relationship between voids and the galaxies they contain is a subject of ongoing investigation. Void galaxies, as they are sometimes called, exhibit distinctive properties that reflect their isolated upbringing. They tend to be smaller and less massive than galaxies in dense environments, having had fewer opportunities to grow through mergers and accretion. The colors of void galaxies are often bluer than those of cluster galaxies. This blueness indicates the presence of young, hot stars, which are short-lived and must have formed recently. In dense environments, gas is often stripped from galaxies by interactions with neighbors and with the hot intergalactic medium that pervades clusters. This stripping quenches star formation, causing galaxies to redden as their existing stars age without replacement. In voids, this stripping does not occur. Galaxies retain their gas reservoirs and continue forming stars at a steady pace. The lack of disruptive encounters allows galactic disks to remain thin and well organized. Spiral patterns persist, untwisted by gravitational disturbances, The Milky Way, though not a pure void galaxy, shares some of these characteristics. Its disk is remarkably thin for its mass. Its star formation continues at a moderate rate, fueled by reservoirs of gas in the disk and in falling clouds. Its spiral arms are well defined, suggesting a relatively undisturbed dynamical history. Whether these properties are directly caused by our environment or reflect other factors is difficult to determine. Galaxy evolution depends on many variables, including initial mass, formation history, and random variations in the accretion of satellites. Disentangling the environmental contribution requires careful statistical comparisons across large samples of galaxies. And this brings us to another quiet detail that connects our local environment to the broader ecology of the cosmic web. The cosmic web is often compared to a living system, with flows of matter analogous to circulating fluids and nodes of activity analogous to organs or processing centers. This metaphor, while imperfect, captures something true about the dynamic nature of the web. Matter is not static. It flows continuously, driven by gravity, channeled by the geometry of filaments and voids. Voids play a particular role in this circulation. They are regions of net outflow, zones where matter drains away toward denser surroundings. The flow is slow on human timescales, but inexorable on cosmic ones. Over billions of years, voids empty while filaments fill, the density contrast growing ever sharper. This process is self-sustaining. As voids empty, they become even less effective at retaining matter, while the surrounding structures become even more attractive. The rich get richer, the empty get emptier. This is a fundamental feature of gravitational dynamics in an expanding universe. The local void participates in this circulation. Matter within it, including the gas and dark matter that make up the majority of its contents, is slowly flowing outward. The galaxies embedded in this matter, including our own, are carried along by the flow, adding their peculiar velocities to the general drift. And this brings us to another quiet detail that deserves exploration. The concept of a void as a region of outflow helps clarify its relationship to the surrounding structures. At the boundaries of a void, where the density transitions from low to high, the flow changes direction. Matter flowing out of the void meets matter flowing toward it from adjacent structures. This convergence creates zones of compression where gas accumulates and star formation may be enhanced. These boundary regions are sometimes called void walls or sheets. They are not solid barriers, but gradual transitions, extending across millions of light years. The galaxies within them occupy an intermediate environment, neither as isolated as deep void galaxies, nor as crowded as cluster galaxies. The transition from void to wall to filament to cluster represents a spectrum of cosmic environments, each with its own characteristic properties. Understanding this spectrum is essential for interpreting the diversity of galaxy types and the processes that shape them. Our galaxy lies somewhere along this spectrum, in a region that is underdense on average, but not extremely so. The local group is not at the center of the local void, but offset from it, closer to the transitional regions that lead toward denser structures. This position exposes us to gravitational influences from multiple directions, creating the complex flow patterns that astronomers have measured. And this brings us to another quiet detail that connects our local environment to the challenge of measurement. Measuring the properties of voids is surprisingly difficult. Unlike galaxy clusters, which stand out as obvious concentrations of light and mass, voids are defined by what they lack. Counting absences is harder than counting presences. Systematic errors can creep into the analysis, biasing the result in subtle ways. One challenge is the selection of galaxies used to trace the density field. Different types of galaxies have different luminosities, and fainter galaxies are harder to detect at large distances. If the survey is incomplete at the faint end, it will underestimate the number of galaxies in certain regions, potentially creating apparent voids where real galaxies simply went unobserved. Correcting for this selection bias requires understanding the luminosity function of galaxies, the distribution of galaxies as a function of brightness. This distribution must be known accurately and applied consistently across the survey volume. Any errors in the luminosity function translate into errors in the inferred density field. Another challenge is the conversion of observed quantities into physical distances. The redshift of a galaxy measures its recession velocity, which includes both the cosmic expansion and any peculiar velocity. In voids, where peculiar velocities can be significant, this conversion is complicated. Galaxies flowing out of a void appear farther away than they actually are, because their peculiar velocity adds to the cosmic expansion. This effect, called redshift space distortion, can artificially inflate the apparent size of voids. Correcting for redshift space distortions requires modeling the peculiar velocity field, which in turn requires knowing the density field. There is circularity here, a bootstrap problem that can only be resolved through iterative analysis or through measurements that do not rely on redshift. These challenges explain why different analyses sometimes produce different results for the properties of the local void. The differences reflect not disagreement about the existence of the void, but uncertainties in its precise parameters. As surveys improve and methods are refined, these uncertainties will shrink, converging toward a clearer picture of our cosmic environment. And this brings us to another quiet detail that deserves attention. The local void is not the only large void known to exist in our cosmic neighborhood. Several other significant underdensities have been identified, each contributing to the complex gravitational landscape that shapes galactic motions. One notable example is a void located in the direction of the constellation Sculptor. This void extends for tens of millions of light years and contributes to the flow patterns observed in our region of space. Its existence was inferred from the motion of galaxies, which showed a component of flow consistent with repulsion from an underdense region. Another example is a void toward the constellation Perseus, on the opposite side of the sky from the major attracting structures. This void is less well characterized than some others, but appears in analyses of the local peculiar velocity field. These multiple voids, distributed in various directions, create a patchy gravitational environment. The Milky Way is influenced by all of them simultaneously, with their individual contributions combining to produce the net motion we observe. Disentangling these contributions requires three-dimensional mapping of the mass distribution, a task that is only partially complete. The interplay between voids and overdensities also affects the interpretation of our motion through space. The apex of the local group's motion, the direction toward which we are moving, is not pointing directly at any single attractor. Instead, it reflects the vector sum of attractions toward dense regions and repulsions from underdense ones. Understanding this vector requires knowing the positions and magnitudes of all significant structures in the vicinity. And this brings us to another quiet detail that connects our local environment to the statistical nature of cosmic structure. The distribution of voids and clusters in the universe is not random. It is structured, governed by the statistics of the primordial fluctuations that seeded all cosmic structure. These fluctuations had specific properties, nearly Gaussian and nearly scale invariant, that determined how likely different configurations would be. Large voids, like the local void, are rarer than small ones. Deep voids are rarer than shallow ones. The probability of finding a void of a given size and depth can be calculated from cosmological theory and compared to observations. If observations reveal more extreme voids than theory predicts, it suggests that something is incomplete in our understanding. Current comparisons show reasonable, but not perfect, agreement. The local void and a few other particularly large structures push against the boundaries of what standard theory allows. Whether this indicates a genuine discrepancy or merely statistical fluctuation is debated. The resolution may come from larger surveys that can characterize the void population with better statistics. If extreme voids are genuinely too common, the implications would be significant. It could require modifications to the initial conditions of the universe, perhaps indicating that inflation produced more power on large scales than currently assumed. Alternatively, it could require modifications to gravity or dark matter, changing how structure forms from given initial conditions. For now, the jury is out. The local void remains an intriguing anomaly, one that may or may not fit comfortably within the standard cosmological framework. Future data will determine which interpretation is correct. And this brings us to another quiet detail that deserves exploration. The study of voids has matured significantly over the past few decades. Early work focused on simply identifying voids and measuring their basic properties, their sizes, shapes, and density contrasts. More recent work has pushed into more sophisticated territory, examining how voids evolve, how they relate to the cosmic microwave background, and how they can be used to constrain cosmological parameters. One particularly promising application involves using voids as standard cosmological probes. Just as Type Ia supernovae serve as standard candles, providing a consistent luminosity that can be used to measure distances, voids may serve as standard shapes or standard dynamics, providing consistent properties that can be used to measure cosmological parameters. The Alcock-Podzinski test, for example, uses the assumption that voids should be statistically spherical in real space. In observations, voids appear distorted by the conversion from redshift to distance. The amount of distortion depends on the cosmological parameters assumed. By adjusting these parameters until the observed voids appear spherical on average, astronomers can constrain the expansion history of the universe. This test has been applied to large void catalogs with encouraging results. The constraints are complementary to those from other probes, providing independent checks on cosmological models. As void catalogs grow larger and more complete, the constraints will tighten. And this brings us to another quiet detail that connects our local environment to the future of observational cosmology. The coming decade will bring transformative new data on the structure of the universe. Surveys like those from the Vera Rubin Observatory will catalog billions of galaxies, mapping the cosmic web to unprecedented depth and completeness. Space missions like Euclid will measure weak gravitational lensing across the sky, directly probing the distribution of dark matter. These data will revolutionize our understanding of voids. They will allow void catalogs to be constructed with higher purity and better defined boundaries. They will enable more precise measurements of void expansion rates, void shapes, and void correlations with the cosmic microwave background. For the local void specifically, new data will refine the estimates of its size, depth, and shape. They will clarify whether its properties are unusual enough to challenge cosmological models, or merely represent a rare but expected fluctuation. They will test whether our local environment can fully explain the Hubble tension, or whether additional physics is required. The anticipation of this new data shapes current research. Theorists are developing more sophisticated models of void formation and evolution, preparing to compare predictions with observations. Observers are refining their analysis techniques, testing them on existing data in preparation for the avalanche of new information. And this brings us to another quiet detail that deserves attention. The philosophical implications of living in a void have not been fully explored. For most of human history, we assumed our position in the cosmos was unremarkable. The Copernican principle, the assumption that we occupy no special location, guided scientific thinking and helped displace geocentric and anthropocentric worldviews. Living in a void complicates this principle without necessarily violating it. We are not at the center of anything, not in any privileged position from which the universe is specially designed for our observation. But we are in an unusual environment, one that affects our measurements in ways that typical observers might not experience. This raises interesting questions about the nature of scientific knowledge. If our observations are filtered through an unusual local environment, how can we be confident that our conclusions apply universally? How do we distinguish between features that are truly cosmic and features that are merely local? The answer lies in careful modeling and cross-checking. We characterize our local environment using multiple independent methods. We quantify its effects on our observations. We compare our results to observations from different vantage points, such as the distant cosmic microwave background. Where these comparisons agree, we can be confident that we have accounted for local effects. Where they disagree, we must look more carefully for overlooked influences. This is the essence of the scientific method applied to our cosmic situation. We do not assume our position is typical. We test it. We measure it. We account for it. And in doing so, we achieve a kind of objectivity that transcends our particular location. And this brings us to another quiet detail that connects our local environment to the nature of cosmic exploration. The universe is too large to explore directly. We cannot send probes to distant galaxies or visit other corners of the cosmic web. Our exploration is necessarily remote, conducted through the photons that reach our telescopes and the gravitational waves that vibrate our detectors. This remoteness imposes fundamental limits on what we can know. We cannot verify our models by visiting the phenomena they describe. We can only compare predictions to observations and accept the models that pass these tests. The local void is part of this observational chain, a feature of our immediate environment that affects the data we receive from the wider universe. Understanding the void is therefore essential for understanding the cosmos. It is not an obstacle to knowledge, but a stepping stone toward it. By characterizing our local environment, we calibrate our observations and improve our interpretations. The more we know about the void, the more reliably we can infer the properties of the universe beyond it. And this brings us to another quiet detail that deserves exploration as we continue our journey through these ideas. The voids of the universe are not all alike. They span a wide range of sizes, from modest underdensities, a few tens of millions of light years across, to supervoids stretching billions of light years. The largest voids are so vast that light takes billions of years to cross them, comparable to a significant fraction of the age of the universe. The local void is large, but not the largest. It is significant, but not unique. Similar voids have been identified elsewhere in the cosmos, each with its own properties and its own influence on surrounding structures. One particularly notable void, sometimes called the giant void or the supervoid in Eridanus, has drawn attention because of its possible association with a cold spot in the cosmic microwave background. This cold spot is a region of the microwave sky that is measurably cooler than its surroundings, an anomaly that has resisted easy explanation. One hypothesis is that the cold spot results from the integrated Sachs-Wolf effect as microwave photons pass through an exceptionally large and empty void. The void would cause the photons to lose energy slightly, making that region of the sky appear cooler. Observations have confirmed that a large void does exist in the direction of the cold spot, lending support to this hypothesis. However, the match is not perfect. Some analyses suggest the void is not quite large or deep enough to produce the full cold spot signal. Other contributions, perhaps from primordial fluctuations or other foreground effects, may be needed to explain the observation completely. This ongoing investigation illustrates how voids connect to multiple aspects of cosmology. They are not isolated phenomena, but integral parts of the cosmic web, influencing everything from galaxy formation to the appearance of the microwave background. Understanding them is essential for understanding the universe as a whole. And this brings us to another quiet detail that connects our local environment to the tools of modern astronomy. The telescopes and surveys that have revealed the local void represent generations of technological development, from the earliest photographic surveys of the 20th century to the digital sky surveys of today. Astronomers have progressively expanded our view of the universe. Each technological advance has revealed new structures and new puzzles. The discovery that the universe is expanding came from measurements of galaxy redshifts in the 1920s. The discovery of the cosmic web came from three-dimensional surveys in the 1980s and 1990s. The detailed characterization of voids and superclusters continues today, enabled by surveys covering millions of galaxies. Future advances will push these boundaries further. Space-based telescopes will escape the blurring effects of Earth's atmosphere. Radio interferometers will achieve angular resolutions impossible for optical telescopes. Gravitational wave detectors will open an entirely new window on the cosmos. Each of these advances will contribute to our understanding of the local void and our position within the cosmic web. They will refine our measurements, test our models, and perhaps reveal surprises that we cannot currently anticipate. And this brings us to another quiet detail that deserves attention. The local void is intimately connected to the question of cosmic variance. Because we observe the universe from a single location, our view is necessarily limited. we see one realization of the statistical processes that generate cosmic structure, not the full ensemble of possibilities. This limitation is called cosmic variance, and it places fundamental bounds on the precision of certain measurements. Even with perfect observations, we cannot know what the universe looks like from other locations. We can only infer statistical properties from our single sample. The local void contributes to cosmic variance in our measurements. If our neighborhood is underdense, our sample of nearby galaxies is not representative of the cosmic average. Corrections can be applied if we know the extent of the underdensity, but uncertainties remain. This is one of the deep challenges of cosmology. We are trying to understand a universe that is too large to survey completely. From a vantage point that may not be typical, the best we can do is characterize our local environment as thoroughly as possible and quantify the resulting uncertainties in our conclusions. And this brings us to another quiet detail that connects our local environment to the nature of scientific progress. The recognition that we live in a void is relatively recent. For most of the history of cosmology, this possibility was not seriously considered. Astronomers assumed that the local universe was representative of the cosmos as a whole, an assumption that simplified calculations but was never rigorously tested. The growing evidence for a local underdensity has changed this perspective. It has forced cosmologists to consider environmental effects in their analyses and to develop new methods for correcting biased measurements. This is scientific progress in action, the gradual refinement of understanding through observation and analysis. The story of the local void is therefore part of a larger narrative about how science advances. Ideas that seem obvious in retrospect were once controversial. Assumptions that were taken for granted were eventually questioned. The picture we have today is the result of countless individual contributions, each building on what came before. And this brings us toward the conclusion of our extended exploration. The local void is a real feature of our cosmic environment. It influences our observations, shapes our measurements, and challenges our assumptions. Understanding it is essential for interpreting the data that cosmology provides. But the local void is also a window into larger questions. It connects to the nature of cosmic structure, the behavior of dark energy, the dynamics of gravity, and the limits of observation. By studying our immediate environment, we learn about the universe at large. This is the beauty of cosmological inquiry. Every local observation has universal implications. Every measurement of nearby galaxies reflects the physics that governs the entire cosmos. The local void, far from being an obstacle to understanding, is an opportunity for it. And so, our exploration continues into the quiet depths of cosmic emptiness, toward an understanding that is always just beyond our reach, but always worth pursuing. The void awaits, and with it, all the questions we have yet to ask, and all the answers we have yet to find. The silence of the void is not truly silent. It speaks in the language of gravity, in the patterns of motion, in the subtle textures of the cosmic web. Learning to read this language is the work of generations, a labor that connects us to everyone who has ever looked up at the night sky and wondered what lies beyond. We are part of that ancient tradition, inheritors of that profound curiosity. The local void is one of the mysteries we have been given to explore, a challenge that rewards patience and precision with glimpses of cosmic truth. This is the universe we inhabit. This is the void we call home. And in recognizing it for what it is, we take another step along the endless path of understanding.